In part 1 of lecture 5, we will discuss multiprogramming and process scheduling criteria. Most modern computer systems use multiprogramming. As a matter of fact, the only systems that do not use multiprogramming are single-tasking systems, like the original PC. Multiprogramming allows us to create the illusion that the computer is doing several things at the same time. In truth, computers are taking advantage of the fact that input and output take much longer than CPU operations. As a result, while the computer is waiting for one process's input or output, it can start work on another process's CPU needs, or at least until it needs I/O. The lifetime of a program can be best described as a series of bursts, where bursts of processor activity are followed by bursts of input-output activity. This cycle is repeated over and over again until the process terminates. Because it is cyclic in nature, we call it the CPU I/O burst cycle. Here is an illustration of the activities that go on in the CPU I/O burst cycle. The green, for go, indicates the CPU burst, where the process is using the CPU to perform whatever instructions it needs to perform. As soon as a request for input or output is indicated, wham! The I/O operation is scheduled and the process gets blocked. Eventually, the input or output operation is finished, and then the process gets back the CPU. It goes through some more instructions until, wham! Another I/O operation, and it is out of the CPU once again. This will continue until the program is finished. One might get the impression from the previous slide that the CPU bursts take as long as I/O bursts in real time, or maybe even longer. This could not be further from the truth. In reality, I/O bursts can be several orders of magnitude longer in duration. This is what makes multiprogramming such a great idea. There are these long waits in which the process is blocked and the CPU can do something else. This illustrates how long it will take if 3 processes are executed without the benefit of multiprogramming. As you can see, the second process can't even start until the first one is completed, even with all that idle CPU time. Here you can see that the second process gets started pretty soon after the first process. They can finish in this example roughly 30% faster. And most of the delay here is due to the need to wait for the other process's input-output operations to finish before the second or third processes can start theirs. If these I/O operations could occur concurrently, using different terminals or different disk drives, we might even see an improvement of 70%. It is worth noting that in examples that are closer to what goes on typically on a computer system, the amount of time that we would save could be far greater than that. There are several factors that help determine choice of scheduling algorithm. Performance criteria. What exactly do we want from our scheduling algorithm? This requires us to look at more specific goals. We want the CPU utilization to be as close to 100% as possible. Obviously, it won't reach 100% of its time running applications, because we may see all of our processes waiting for input-output, and the operating system will take up some of the CPU's time as well. But we want to get as close to 100% utilization as possible. We really want to maximize our throughput, the number of finished processes per unit time. Maximum throughput is a realistic goal, and one we can easily achieve. The inverse of throughput is turnaround time, the time interval between submitting a job and when the final results of that job are received. Turnaround time is a term usually associated with batch processing. Its equivalent in interactive systems is response time, the time interval between starting or resuming a program and when we receive our next response from the program. We also want to minimize the time our processes spend waiting for the use of the CPU. Scheduling can be preemptive or non-preemptive. Preemptive scheduling means that a process can be moved out of the CPU by the system. Most modern operating systems use it, especially for short-term scheduling. Non-preemptive scheduling means that while the process can give up the CPU voluntarily by terminating, aborting, or being blocked so that I/O can be performed, it cannot be bumped out for other reasons. There is another term that is important to understand before we start talking about CPU scheduling. Starvation refers to a situation where a process waits indefinitely for the CPU without ever getting to use it. This can also refer to the scheduling of I/O operations. This is extremely undesirable and something that we will seek to avoid.